This is Mr. Craig with the last example, and this is an interesting one, but you will be asked about drawing Lewis structures like this as well. Still go through the same process here, determine how many valence electrons we have. Magnesium is in group 2, so we have 2 from magnesium. Chlorine has 7 each, and we have 2 of those. So we have a total of 16 electrons. Now, since we have 16 electrons, what I don't want you to do is put the magnesium in the middle and then start sharing electrons. I need you to recognize that we have a metal with a nonmetal. If you have a metal with a nonmetal, what kind of substance do you have? That's right, we have an ionic compound. So, when allocating who gets electrons and who doesn't get electrons, we need to be very smart about this. Magnesium is a metal, and as a metal, metals want to give away their electrons. Magnesium brought 2 electrons with it, and what we're going to do is give those 2 electrons away. For that very reason, we need to show brackets. Brackets indicate 2 things. The first thing is that we have a different number of electrons from that which we started. Magnesium brought 2 valence electrons, and it gave each of the chlorines 1 of its valence electrons. You don't need to do that. Just know that magnesium gave away its electrons. The second thing is, since it has a different number of electrons from that which it started, we have to tell everybody how many it gave away or took on. So magnesium should have no valence electrons because metals give away their valence electrons. Chlorine, however, had 7 electrons to start with, and magnesium gave each of the chlorines 1 electron. So we need to draw a bracket around each chlorine as well after we have given it its electron, because again, chlorine has a different number of electrons from that which it started, and we have to tell everybody how many it either gained or lost. This is the best Lewis structure that we can draw for magnesium chloride. Now, if you want to put magnesium in the middle and the chlorines over here, that's fine. It doesn't matter, because again, they are not sharing electrons, so it doesn't matter how you arrange this. Besides, if we were going to actually determine what this looked like, we would have to do something with a cubic U, or a unit cubic. So don't worry about how your Lewis structure is arranged. Just do realize that the metals will have their own bracket, the nonmetals will have their own bracket, and then we'll indicate what the charge is based on how many electrons either donated or accepted. Alright, so we have our correct Lewis structure. Valence or Vesper shape. Well, good news, with ionic compounds, you don't have to worry about Vesper shapes. Vesper only deals with compounds that are sharing electrons, so no Vesper. Next thing, hybridization. Same thing. No sharing of electrons, no hybridization. In other words, the chlorine has beautiful s and p orbitals because they're not sharing electrons. So no hybridization. Sigma and pi bonds. Guess what? No sharing of electrons, no sigma, no pi. Indicate whether it's a polar or nonpolar compound. All ionic compounds, up to this point, are very polar. Now again, there are some degrees of how much something will dissolve in water. We'll talk about that later. But right now, if it's an ionic compound, we're saying it's polar. Type of intramolecular forces, right here. We have an ionic compound. We have a metal with a nonmetal. So we have ionic intramolecular forces. The type of intermolecular forces, life is good with ionic compounds, metal with a nonmetal. So it also has ionic intermolecular forces. And last but not least, the type of solid, ionic. So when you go and tell me what type of intramolecular, intermolecular, and solid type, the answer is ionic. I hope this has helped. I'm going to make another video with more examples here. So stay tuned.